Imagine a messenger arriving not from another country, not even from another planet, but from another star system. That is what 3I/Atlas really is, a frozen traveler born far beyond the edges of our sun's influence. For the second time in human history, after Oumuamua and Borisov, we are watching a true interstellar visitor. Every telescope that looks at it finds something new. Instead of answering our questions, 3I/Atlas creates new ones, each stranger than the last. And these questions are not just about astronomy. They touch on life, origins, and even humanity's place in the galaxy. Scientists have already outlined 5 main problems, 5 puzzles that this comet leaves us with. Let's go through them one by one. Astronomers expected 3I/Atlas to behave like a normal comet, mostly water ice with carbon dioxide and other gases in smaller amounts. But when the James Webb Space Telescope studied it, the result was shocking. The comet contained about 8 times more CO₂ than H2O, making it one of the most carbon dioxide-rich comets ever seen. In our solar system, comets usually start releasing water when they come within about 3 astronomical units of the Sun. Water dominates, with CO₂ playing a smaller role. But at 3.3 astronomical units, 3I/Atlas was already producing a coma where carbon dioxide was the main component and water was secondary. This inversion suggests either a very unusual internal composition or a surface structure that lets CO₂ escape more easily. Both challenge current comet models. Such chemistry hints that 3I/Atlas formed under conditions unlike anything in our solar system. Perhaps it was born in an extremely cold disk, rich in carbon dioxide, or in a star-forming region with very different radiation and chemistry. Even stranger, carbon dioxide is volatile and should not survive a billion-year drift through interstellar space, yet here it is, preserved. That means interstellar comets may carry hidden reservoirs of fragile chemistry, perhaps even organics across the galaxy. This has implications for humanity. Comets may have delivered Earth's water and the ingredients of life. If interstellar comets carry radically different recipes, then every planetary system might be seeded with unique chemistry, shaping worlds in unpredictable ways. Some scientists even suggest such comets help build giant planets by delivering frozen gases to young systems. The deeper mystery is that observations show not only carbon dioxide and water, but traces of carbon monoxide, carbonyl sulfide, and dust. And still, nothing explains the imbalance. 3. I/Atlas challenges our models and forces us to admit that cosmic chemistry is more diverse than we thought. So the first great problem of 3I/Atlas is not danger but uncertainty. Its chemistry shows us that the galaxy is a laboratory of strange experiments, and we have only just begun to read the recipes. When you think of a comet glowing green in the night sky, the explanation usually sounds simple. Sunlight hits molecules of diatomic carbon, C2, and they release a greenish light. Astronomers have seen this for more than a century, and it has become almost a rule. Green glow means C2 is there. But 3I/Atlas broke this rule in a dramatic way. At first, as it drifted inward, its coma looked reddish, the normal color of dust scattering sunlight. Then telescopes caught something unusual. The clouds surrounding the comet began to shift to a blue-green hue. For observers, it was a striking transformation. Naturally, scientists checked for C2, but the expected spectral lines were weak, almost absent. In fact, the comet seemed to be depleted in C2 and other carbon chain molecules, so how could it glow green without them? This puzzle quickly spread through the astronomy community. Some proposed cyanogen, CN, a molecule of carbon and nitrogen, might be responsible, since it was detected in larger amounts. Others suggested the glow came not from molecules, but from tiny icy grains scattering sunlight in unusual ways. A few argued that unique interstellar chemistry, reactions shaped outside the solar system, might be producing the effect. None of these explanations is fully convincing yet. Why does this matter? Because light is our main tool in astronomy. We do not send spacecraft to every comet. Instead, we read spectra, the fingerprints of molecules carried by photons. If a nearby interstellar visitor can confuse us so much, what about the thousands of exoplanets we study the same way? The green glow problem is not just a cometary curiosity. It warns us that alien chemistry may trick our interpretations, making us think we see one molecule when another is really at work. For humanity, this is both unsettling and exciting. It means the universe is chemically richer than our textbooks, and interstellar comets could be messengers carrying ingredients we have never encountered. They might even deliver exotic ices or organics to young planets, shaping environments in unpredictable ways. And on a cultural level, the image of a comet glowing green has always stirred emotion. In the past, people saw such lights as omens. Today, we frame them as natural science. Yet 3I/Atlas reminds us that even the natural can remain mysterious. Its glow is not just pretty to look at, it is a question mark hanging in the sky. So the second great problem of 3I/Atlas is this. We thought we understood the light of comets, but this one refuses to play by the rules. Astronomers often study comets through polarimetry, measuring how light waves change orientation after bouncing off dust grains. This reveals the size, shape, and structure of the particles. Normally, comets show a mild dip in polarization at small phase angles, called the negative polarization branch. It's predictable and consistent across solar system comets. But 3I/Atlas broke the pattern. Telescopes recorded a much deeper negative polarization, around minus 2.7% at 7 degrees. To specialists, this was shocking. No other comet or asteroid had shown such extreme behavior. The result means its dust interacts with light in a way alien to us. The grains may be unusually small, porous, or coated with exotic ices. Whatever the cause, they are fundamentally different from anything observed locally. Why is this a problem? Because dust is the foundation of planets. If interstellar grains scatter light in unexpected ways, then our models of planet formation may be incomplete. Polarimetry is also key for studying asteroids, dust clouds, and exoplanet atmospheres. So if exotic chemistry bends light differently, we must be careful not to misread our data. For the public, it helps to imagine shining a flashlight into smoke and watching the light twist and fade in strange colors. That's what astronomers saw with 3I/Atlas, light that refuses to follow the rules. Thus, the third problem is clear. Its dust shows us that not all cosmic matter behaves like the matter we know. The galaxy holds materials our physics still struggles to explain, and they may be the very building blocks of new worlds. In the solar system, we know the family trees of objects. Planets from the protoplanetary disk, asteroids from its leftovers, comets from the Kuiper belt and Oort cloud. But 3I/Atlas is different. Its hyperbolic orbit shows it is interstellar, simply passing through before leaving forever. Where it was born remains a mystery. Astronomers try to trace its path backward, but uncertainties in speed make its exact origin unknowable. Was it ejected by a giant planet in a young system or thrown out near a star-forming region? Each scenario is possible, but none can be confirmed. Then comes the question of age. Interstellar comets like 3I/Atlas could be billions of years old, perhaps older than Earth. Imagine a frozen fragment drifting for eons, battered by cosmic rays yet still carrying the chemistry of another world. That survival alone is remarkable. For humanity, this raises two problems. First, without knowing its birthplace, we cannot compare its chemistry to a specific star or system. Second, its immense age suggests that such comets may be common travelers, linking star systems and spreading raw ingredients of life. This connects directly to panspermia, the idea that comets can carry water, organics, or molecules between worlds. But here lies the frustration. We cannot study its past directly. Without a mission to capture its material, most of its story will vanish as it departs. So the fourth problem is this. We do not know where 3I/Atlas came from, nor how old it truly is. It reminds us that the galaxy's history is largely invisible, revealed only in brief visits from wanderers like this one. When astronomers first plotted the orbit of 3I/Atlas, one fact stood out. It is moving on a hyperbolic trajectory. That means it is not bound to the sun. Unlike comets from the Oort cloud, which swing back after thousands of years, this one is just passing through. It entered the solar system from interstellar space, and after a brief encounter with our star, it will continue on, vanishing into the dark. On paper, that sounds simple, but in reality, its path is not perfectly predictable. Every comet's orbit changes as it approaches the sun, because the heat triggers jets of gas and dust that push on the nucleus like tiny thrusters. With 3I/Atlas, the effect is even harder to model because its chemistry is unusual. The strong release of carbon dioxide, the uneven jets on the sunlit side, all of this introduces uncertainty. Will it pass exactly where our calculations expect, or will it drift slightly as it outgasses? Even a small change can alter its course over millions of kilometers. This unpredictability is not dangerous for Earth in this case. Current measurements show that its closest approach keeps it far away, at a distance of about 1.8 astronomical units, safely beyond the orbit of Mars. But the problem for humanity lies in the principle. We cannot yet fully model interstellar comets. We do not know how their surfaces behave under solar heating, how their ices sublimate, or how their structures respond to stress. Without this knowledge, our predictions are always approximate. And there is another layer. As 3I/Atlas passes near Mars, the Sun, and eventually the outer planets, it feels their gravity. Each encounter, even if distant, can bend its path slightly. For a comet moving at interstellar speed, even small nudges accumulate. Tracing its exact trajectory into the future becomes like predicting the flight of a leaf in a storm, possible in broad strokes but messy in detail. For planetary defense, this uncertainty is a warning. Today, 3I/Atlas is harmless. But what if the next interstellar comet takes a closer path? If we cannot model its motion precisely, we risk underestimating or miscalculating. Humanity's ability to respond to cosmic threats depends on prediction, and interstellar visitors expose the limits of that ability. There is also the philosophical side. Watching a body that will never return forces us to confront impermanence. Every comet from the Oort cloud belongs to our sun's family. It will be back someday. But 3I/Atlas is a true stranger. Once it leaves, it is gone forever, carrying its mysteries with it. The uncertainty of its path is also the uncertainty of our chance to learn from it. We have only this brief encounter, this small window in cosmic time. So the fifth great problem of 3I/Atlas is not danger, but knowledge. Its path is uncertain, and with it, our opportunity to understand. It challenges us to improve our models, to prepare for the next visitor, and to accept that some mysteries may slip away into the night sky before we can solve them.